All right, let's do a midterm. Okay, so we have question 1. We had 3 parts. The first is give an example of a vector space over R without a finite basis. Okay? So there are a lot of examples here. So one of the ones I think we saw in the lecture was if you can take the set of functions from the natural numbers to R. This is just a set of revalued sequences, and you add and multiply component-wise. Okay, so f plus g of n is f of n plus g of n cf of n is, well, just c times f of n. Okay? See that there's no finite basis. Note that there's countably many linearly independent vectors. Okay? Of the form 1 and then all zeros, or 0, 1, all the zeros, and continue. Okay? And if there was a finite basis, then this space would be isomorphic to Rn, and, well, there can't be, you could be able to find, more linearly independent vectors than what's allowed in Rn. In fact, this is just an aside. There's no countable basis here. Okay, you might think this works as a basis, but not every vector will be a finite linear combination of these vectors. Okay, for part 2, we needed linear transformation from R2 to R2, which is not invertible, but infinite image. Okay, so a perfectly good example here is projection onto the x-axis. Okay, so the matrix is 1, 0, 0, 0 in the standard basis. So it's not going to be invertible because this isn't a bijection, but still we'll have image an entire line. All right, and finally part 3, we want a non-trivial linear transformation from R2 to R2 with a squared being 0. Okay, so the previous example doesn't work because t squared is just t, right? But I'll just write down the matrix, 0, 1, 0, 0. Okay, this will have the property that it squares to 0. And the point is that what this transformation does is send x to y and send y to 0. So therefore, if you look at the square, well, x will go to y, and that will go to 0, and then y will go to 0, and that goes to 0. Okay, so on to question 2, which asked, can an invertible matrix, or it said prove the invertible matrix A prove it cannot have a to the n being 0 for any n and n. Okay? So the proof is going to be, actually, we prove that a to the n is an invertible matrix. Okay? And the 0 transformation, so the corresponding to this matrix with all zeros, is not invertible. Okay, so you can think of this as, what we're saying is a composition of invertible matrices is invertible. So if we want to prove this, well, I guess we can first say that if we have A and B, two invertible matrices, then the inverse of AB is B inverse A inverse, since we have AB times B inverse A inverse is the identity, okay? And therefore, by induction, so we're going to write AN to be A times AN minus 1. This is going to be invertible by induction. And this one is invertible by assumption. So we get that A to the N is invertible. All right, and for the invertible matrix, A not equaling the identity, but A squared equal to the identity, well, there's a lot of options. I'll just give a 2 by 2 example. Actually, you can just do a 1 by 1 example. So the matrix is just going to be negative 1, 0, 0, negative 1. Okay, so this sends x to minus x, y to minus y. When you square it, it's the identity. All right, question 3. So now we have to solve a system of linear equations. So we have 2x plus y plus 3z is 2, negative x plus y plus 5z is negative 1, and x plus 3y plus 2z is 2. Okay, so we're going to write this out using this coefficient matrix and the vector that we want. Put this coefficient matrix in echelon form and then solve. Okay, so we get 2, 1, 3, negative 1, 1, 5, and 1, 3, 2. Okay, so actually what I'm going to do just to make it easier in my head is switch the rows. So I'm going to bring this row up. Okay, so row 3 switches with row 1. So we get 1, 3, 2, 2, negative 1, 1, 5, negative 1, and 2, 1, 3, and 2. Okay, so this is just to make canceling this column easier. Okay, so then we're going to add row 1 to row 2, and add negative 2 row 1 to row 3. Let's see what this gets us. So the first row stays the same. Now we're adding, so we get 0, 4, 7, 1. Then we're subtracting 2, so we get 0, negative 5, negative 1, negative 2. Okay, now we want to cancel this term. So we're going to add 5/4 of row 2 to row 3. I'll put this down here. So we get 1, 3, 2, 2, 0, 4, 7, 1, 0, 0, 31 fourths. And let's see, 5 fourths. That minus 2, so negative 3 fourths. All right, so now we get x3 is equal to negative 3 over 31. We have 4x2 plus 7 times negative 3 over 31 is equal to 1. So we get x2 is equal to 13 over 31. And finally, we have x1 plus 39 over 31 plus, minus 6 over 31 is equal to, I'll say 62 over 31. So we get x1 is 68 minus 39, so we get 29 over 31. Okay, so maybe I did not pick the best numbers, but we got the solution. All right, I should mention, I mean, I'm sure this is probably quite well known, but you should never get one of these problems wrong because you can check your answers. Okay, so make sure you didn't make algebra mistake. Okay? Okay, so on to question 4. So we had to prove whether or not the following functions were linear transformations. Okay, so the first one went from n by n matrices to R, and this sent a matrix Aij to the sum of its values. Okay? Okay, so this turns out to be linear. Okay. So to prove this, we take a linear combination of matrices. So I'll say alpha 1 A1 up through alpha n AN and apply F. Okay. So first off, what this matrix is the ijth entry is alpha 1 Aij1 plus alpha n Aijn, where Aij1 is the ijth entry of Ai. So therefore, F of this linear combination of matrices is a sum over all I and j of these terms. We get another sum, so I should probably have, okay, I'll make this k equals 1 to n, alpha k, ai, j, k. Okay, so now we can switch the order of summation. So we get the sum from k equals 1 to n of alpha k, sum over I and j, a sub ij to the k. And this is precisely the sum from k equals 1 to n, alpha k, f of ak. So in short, we're taking a matrix to a large sum. When you take a linear combination of matrices, you're getting a linear combination of those sums, and that's the same as the sum of the linear combinations. Okay, so for the second one, we had Pn is polynomials of degree less than n. And then we had the map, which sends f of t to the derivative of t plus 2. Okay, so this is not linear. We can just give a specific example. One example would just be the 0 function, because it goes to 2, and it should go to the 0 function. I'll just give another example. If I take f of, say, t is 1 plus t, then this goes to 3 under this function. On the other hand, if I take 2 times 1 plus t, this will go to 4, okay, which is not equal to 2 times 3. Okay, so just as a side, you have to be a little, be careful about linearity. Is not always preserved by addition in some sense. So this kind of looks like a linear function because you're just adding something to a linear function, but adding a non-zero vector is not a linear operation. Okay, so let me do question 5. So this was true, false. So the first one was a subset of a linearly independent set is linearly independent. Okay, and this is true. Okay, and the proof or the reason is that a trivial linear combination on the subset, or of vectors in the subset, extends to a non-trivial linear combination on the whole set. Okay, so in other words, if you have some linear combination of vectors, which is non-trivial, which has a non-trivial coefficient and is equal to 0, then you just, put 0 in front of the other vectors, and you'll get something which is non-trivial linear combination for the whole set. Okay, so if there's a linear dependence relation on the subset, we get one for the whole set, but since our whole set's linearly independent, we can't have one on the smaller set. So the second one is the same for spanning, this is false. So a subset of spanning is spanning. And this is false. I'll just give a specific example. We can take R2 spanned by 1, 0, and 0, 1, and 1, 0 is not spanning. Okay. All right, so the other one, last one, is if I take an invertible matrix, then is the trace of A inverse equal to 1 over the trace of A. Okay, so this is false as well. Again, I'll just make an explicit example. Okay, so if you look at the matrix 2, 0, 0, 2, this is invertible and the trace is 4. On the other hand, its inverse is a half, 0, 0, a half, which gives you that the trace is 1. Okay, so essentially anything that you put works, but of course it's not, this is true if A is just a 1 by 1 matrix, so you have to be a little bit careful. Okay, finally for question 6, we had an orthogonal matrix. Satisfies the relation A transpose is the same as its inverse. Okay, so we had a couple parts. So first we had to show that product of orthogonal matrices is orthogonal. Okay, so let's see why this is. Well, if we take AB inverse and AB I'll just do it this way. This is B inverse A inverse. Okay. Since A and B are orthogonal, this is B inverse A inverse is equal to B transpose times A transpose. And then by product, so transpose, this is AB transpose. Okay, so that's why, and this is just what we want to show for AB being an orthogonal matrix. To show rotations around the origin are orthogonal, well, we have the general formula. We have cosine alpha sine alpha, negative sine alpha, cosine alpha. And then its inverse, so the inverse is cosine of minus alpha minus sine minus alpha, sine of minus alpha, cosine of minus alpha. So you can write down this explicitly, or you can say, you know, this is rotating by the same number of degrees in the other way. So if you compose, they're going to be obviously the identity. Okay, and then by law of sines or cosines, you get, this is the same as cosine, cosine sine alpha minus sine alpha, which is exactly the transpose. Okay. Finally, for an invertible matrix that is not orthogonal, okay, so I'll just use my example from last time since that's perfectly good. Okay, so this is A transpose is equal to A. On the other hand, A inverse is equal to this matrix, so A transpose is not equal to A inverse. Okay, so that is that.